introduction. So my talk will basically be about polytopes and their volumes, number of lattice points, how to go back and forth from one to the other, and related combinatorial structures. Okay, yeah, there are two parts. In the first part, I will give a lot of examples, and in the second part, I will explain everything in detail. Let's start with very simple examples. So suppose you have a lot of these 2-cent and 3-cent coins, which were in use at some point, and you want to pay someone 10 cents. Then you can ask, how many different ways can you kind of split the sum of 10 cents as a sum of these two types of coins? The answer is very simple. There are two different ways of doing this: 5 times 2 or 2 times 3 plus 2 times 2. And this is a very classical problem, this coin exchange problem, studied already in the 19th century. Yeah, let's look at this a bit more systematically. So if we replace 10 cents by n, we are interested in finding non-negative integers a and b. So it's 2 times a plus 3 times b is equal to n. And if you think about this problem for a bit, then one can figure out that the number of non-negative integer solutions a and b to this equation is given by this formula. So you can see that it's kind of essentially linear in n, but there is some kind of periodicity. You get different linear polynomials depending on which coset modulo 6 you are in. And this can also be written in closed form, and you should know that there are like some roots of unity appearing in this formula which give you exactly this periodicity. Yeah, let's look at this problem again, now from a geometric point of view. So non-negative integers a and b satisfying this equation corresponds to integer points in this polytope, well, this one-dimensional polytope, which I've drawn right here. And remember, there were, for n equal 10, there were two solutions which corresponds to these two integer points here. And yeah, for if we make n bigger, then this corresponds to kind of shifting the polytope a bit. Yeah, now that we have a geometric object, a polytope, we can also look at its volume. And well, these are like one-dimensional polytopes, so we want to look at a one-dimensional volume, also called length. And we want to normalize this volume such that like the distance between two lattice points, like this segment here, is 1. And then when we see for n equals 18, we get a polytope of length 3. So the formula is n over 6, and this works in general. And then recall that we have the number, this formula for the number of integer points, and you can ask what is the relationship between the two. And one obvious remark is that they're kind of roughly the same. This one is n over 6. This is a term which starts with n over 6, and then some kind of lower, well, some essentially constant or periodic terms follow. And slightly more complicated relationship is that we will generalize later on, is that if you take this function and you apply this rather complicated looking differential operator to it, then you get this one. So here the 1 tells you you should keep the n over 6. This 1 tells you, gives you kind of the level as well, and then the rest gives you this periodic part. Okay, let's look at something a bit more general. So now suppose instead of having like a lot of coins, we're given 3 vectors, 1, 0, 0, 1, and 1, 1. And we want to write another vector in V2 as a sum of these 3. Again, this kind of has some geometric interpretation, corresponds to integer points in this polytope. There are like 3 variables here. There are 2 equations. 3 minus 2 is 1, so we get kind of a one-dimensional polytope here. And yeah, and again we can kind of have a function I which counts integer points in this polytope, and a function t which counts some measures some normalized volume in these polytopes. And yeah, here are some examples. So obviously, if the arguments u and v are negative, then there is kind of the polytope empty. And then in this positive quadrant, the formula for the number of integer points is the minimum of u plus 1 and v plus 1, and the volume is always a bit smaller, and you kind of see that it kind of agrees piecewise with polynomials, so on like each of these cones, two cones here, there are different polynomials. And again, we have kind of some differential operator which transforms this function into this one, like 1 plus differentiation direction u plus differentiation direction v. And one problem about this is that it's kind of not always well defined. So on this kind of dotted red line here, if you approach points from the left, from the right, and you apply this operator, you get 1. If you approach points from the left, you get 0. So it's kind of discontinuous there. But what you can always do is just plug in u minus 1 and v minus 1 into this function I, and then you get t. And yes, that was the introduction. Now we start with some definitions and theorems. So the general setup today is that we always have a list of n vectors, or equivalently, these are like the columns of a d by n matrix. We always assume that d is less or equal than n, and the matrix has full rank. So these are the two examples that we have seen. And furthermore, we want that 0 is not in the convex hull of the vectors, or put differently, like all vectors lie on one side of a hyperplane. Otherwise, these polytopes pi sub x won't be, well, they will be unbounded, so they're not polytopes. And yeah, sometimes we will assume that this list of vectors or matrix is unimodular, which means that every non-singular d by d submatrix has determinant plus or minus 1, or equivalently, if we choose a basis for the vector space from these vectors, then this is already a lattice basis. And well, this is an example of a unimodular matrix. This is an example of a non-unimodular matrix. Well, in this example, we can use like periodicity. Here we do. Okay, more definitions. So, well, again, we define these partition polytopes, pi sub x for the list of vectors x and some argument u, which is just the set of points in the positive quadrant such that x tends alpha is u. And then again, we define this function t sub x, which measures the volume of these polytopes. So they're always n minus d dimensional. So we take n minus d dimensional volume, and then we have some normalization factor here. And we have the vector partition function, which again counts the number of integer points in these polytopes. And yes, I want to remark that this vector partition function generalizes our polynomials. Okay, a few remarks on these functions. So the support is always the cone spanned by the vectors in the list. And t sub x is, well, piecewise polynomial function, and each of these local pieces is a polynomial of homogeneous polynomial of degree n minus d. And the regions of polynomiality, there are cones spanned by also some of these vectors. So here are some examples. And yeah, the ix, which counts integer points, is a bit more complicated, of the kind of a piecewise defined function, but in general it's only quasi-polynomial, which means that we choose some like sublattice of our integer lattice, and then on each coset of this sublattice is agreed with a polynomial. And if the matrix is unimodular, it's actually polynomial. Okay, one more bit of notation. So for now, this x is a vector with like coordinates v1 through vd and r to the d, and this defines defines a linear polynomial p sub x, where we just take each of the entries as coefficients for variables s1 to sd. Here's an example. The vector 1, 2 just defines the polynomial of s1 plus 2 s2. And yeah, now we can define this Todd operator, which is a Formal power series in d variables. We just take the product over all the vectors in our list x, and then for each one we take the polynomial defined by this vector and divide it by 1 minus e to the minus px. And the iterational function here, they have an expansion in terms of Bernoulli numbers. This is actually one of the ways one can define the Bernoulli numbers. And then if we are given such a polynomial p or a formal power series p, then I will write p of capital D to denote the differential operator obtained from this by just replacing each of the variables by partial differentiation in this direction. And here's a very classical theorem of Khovansky and Tukhlikov. So if the matrix is unimodular and we have some vector in the lattice, and we take the local piece of the multivariate spline near this vector, and then the theorem says that we obtain the number of integer points, or like this polytope defined by the parameter u, by applying this Todd differential operator to this local piece. And we have to take a local piece here, since this is kind of only piecewise polynomial, so like where the regions of polynomiality overlap, it's not sufficiently smooth to apply this operator. And okay, some remarks. So Tx, as I said before, is a polynomial of degree n minus b. The Todd operator has infinitely many terms, so almost all of these terms are obviously irrelevant, and kind of throwing away everything above this degree would be okay, but one can actually throw away more. And before I tell you about this, let me remind you about zonotopes. So the zonotope is a polytope defined by a list of vectors, which is just kind of the image of a unit cube under this list of vectors, under this matrix. And I will denote this set of interior lattice points of the zonotope by this script, the sort of minus. Here's an example of the zonotope from here, interior lattice points. Okay. So yeah, let me recall for vector x, we defined a linear polynomial e sub x, and then also for a list of vectors y, we can define a homogeneous polynomial p sub y. It's just kind of the product of all these linear guys. For example, if we have the vector 1, 0 and 1, 2, then we would get this homogeneous polynomial. And yeah, then we have this central p-space, which was first studied by people in approximation theory. So we would kind of run over all sublists y sub x, such that their complement still has full rank, take the corresponding homogeneous polynomials, and then take the vector space spanned by all these guys. So here's an example that the list of vectors is like 1, 1, 1. We are kind of allowed to take the empty lists and the one-element sublists and the two-element sublists, which give us kind of this, but we're not allowed to take the whole list because then the rank would, the complement drops. So this is p-space. And one can actually project like formal power series to this p-space, such that if we kind of apply this projection to the Todd operator, it still kind of does the same on the multivariate spline. So this is projection to kind of the relevant part of the Todd operator. And in the example, we would kind of just throw away all monomials of degree at least 3. In general, it's a bit more complicated. Yes, one more thing. In my example before, I showed you that like this, if we apply this Todd operator to the multivariate splines, there are kind of regions where this is not well defined. And so this is why we introduce this internal p-space. example that I showed you before, we would, well, if we remove one element here, we have two ones. So each of these corresponding central key spaces just contains like the one polynomial of degree at most 1. And yeah, this my first theorem, like this internal key space is exactly the space of differential operators with constant coefficients, which leaves this spline continuous. And yeah, more stuff. So now we kind of shift this tot operator a bit. We take some vector, we take the corresponding linear polynomial, take the exponential of this, multiply it by tot, and then project to the key space. We get this polynomial f sub z. And yeah, some results. If we have a unimodular list and that is an interior lattice point of the zonotope, then this guy actually lives in the internal key space, which was kind of the subspace of the central key space, which is nice. So this term, this is actually well defined, since for this operator in the internal key space, so at least by the previous theorem, this function continuous. And then we get kind of, if we apply this, we get the vector partition function with some small shift, which just comes from this exponential. So this is kind of a nicer version of the Kowalski-Bublikov theorem, which holds globally, where we don't have to use a local piece. And here, one more result, all these have that form a basis for the internal key space if we run over all interior lattice points of the zonotope. Okay, yeah, matroids in my title. So here is some, let me recall, these are graded vector spaces, so they have a Hilbert series which keeps track of the dimensions of the local pieces. Matroids have been defined several times today before. And one important thing is that matroids come with a Tutt polynomial, which can be defined in various ways. This is one of them. And well, this keeps track of like a lot of interesting information about the matroid. In particular, it also tells us something about the Hilbert series of these key spaces. So, well, the internal key space is an evaluation, the Hilbert series of the internal key space is an evaluation of the Tutt polynomial, and the internal, the Hilbert series of the central key space is also an evaluation of the Tutt polynomial. And, well, this is kind of related, this evaluation is related to the chromatic, characteristic polynomial of the dual matroid. And this one is related to the, well, to the H polynomial of the matroid complex of the dual matroid. And then it's kind of just the general theory of Tutt polynomial and matroid that in the unimodular case, these evaluations, well, we get from these two results that the dimension of the central key space equals the volume of the zonotope, and the dimension of the internal key space equals the number of interior lattice points of the zonotope. Okay. Now, yeah, everything so far at this condition, the matrix has to be unimodular. And now in the remaining 4 minutes, I will tell you about what to do if the matrix is not unimodular. Then we have to, well, then as we have seen before, like the vector partition function was periodic, so we need like something which gives us its periodicity. And for this, we need toric arrangements. So recall that, well, a vector in R to the D defines a hyperplane, 2, 0 defines some hyperplane, going to the origin. And we can also kind of look at this, do the same thing on torus, so the real torus. Take all vectors phi, so that phi times x is 0. And on the torus, this vector 2, 0 gives us like two well, hyperplanes. So this gives us of a disconnected hypersurface. And the vector 3, 0, 3 even gives us 3. And these arrangements come with vertices, which are like zero-dimensional intersections of a few of these guys. And the hyperplane arrangement just has one. The toric arrangement has a few more. And yeah, we'll denote the set by vertices by v of x. And each of these vertices defines a map from R to the D to the kind of one-dimensional sphere living in C by just taking the exponential e to the pi I of phi times x. This is a periodic function, and this is a higher dimensional analog of a root of unity. And then using this, one can kind of define a periodic Todd operator, which is a, well, looks rather complicated. It's the sum over the vertices of the toric arrangement and then some kind of terms which look like the usual Todd operator. And this kind of does what it's supposed to do. So as in Khovansky-Pukhlikov, we can take a local piece of the multivariate spline, apply the periodic Todd operator to it, and get the number of integer points. And this works, even if the matrix is not unimodular. And as before, we can kind of, this Todd operator is very long, and we can make it a bit shorter, and kind of define these periodic central piece spaces, which are direct sum over, like, we sum over vertices of the toric arrangement, and then we kind of get some smaller local piece spaces there. And there's also some like projection from like the space where this general Todd operator lives into the central piece space, such that kind of this projection only cuts off the irrelevant part. And we can also kind of do this shift again of the Todd operator by some lattice point. Define some f sub z tilde, and all these guys span the internal periodic piece space. And then we kind of get all the theorems again that we have seen before. So like the spaces in the internal periodic piece space are exactly the ones, the operators that leave the spline continuous. And we kind of get a nicer version of the Briand-Vernier formula, which also has this shift. And yeah, here's a question to the audience. So Khovansky-Pukhlikov and Briand-Vernier had like a mainly geometric motivation for proving their theorems. For example, Khovansky-Pukhlikov's formula is equivalent to the Riemann-Roch theorem for smooth toric varieties. And yeah, my question is if like any of my results here on these piece spaces have any interpretation in terms of toric varieties or algebraic geometry. So maybe somebody here knows more about toric varieties than me. And yeah, let me speak for 1 minute about like the analog of the kind of matroid results. So I think at the last 3 FPSACs, Luca Mochi always gave talks on arithmetic matroids, which are kind of essentially matroids, but we also have some multiplicity function defined for each subset of a ground set. And then we have an arithmetic Tott polynomial, which just looks like the normal Tott polynomial, but we have this multiplicity function here. And well, if the matrix is unimodular, both are the same. And kind of for the things that I'm studying, the arithmetic matroid is kind of the proper combinatorial structure which captures the combinatorics of these results. So here's kind of the simple thing that like the dimension of these spaces, actually we need to speak about this first. So like the Hilbert series of these periodic piece spaces are kind of exactly the same evaluations of the Tott polynomial as like on my previous slides on Tott polynomials. And also we have this kind of connection between the dimension of these spaces and zonotopes, which holds in general and not only for the unimodular case. Okay, and I think that's it.
related to these remarkable spaces of De Guccini, Processi, and Bern?
No, I don't. Do you mean the DPV?
Yeah.
Well, they have the same dimension, but yeah, well, these are kind of honest vector spaces. I think the DPV spaces are just kind of, they're very complicated. But yeah, I've looked at this. But I think there's no obvious connection.
Questions? Okay, let's thank Matthias again.